Hello, this is Teach Nichols, and this video in our thermodynamics unit is on thermodynamic systems and entropy. The essential question for this video is, how do we define the thermodynamic system, and how or why does the energy move around inside a closed system? So in order to understand what's going on with thermal systems, we're going to have a new kind of energy we're going to define, and that's going to be called thermal energy. I wish energies were all E with subscript, but they're not. They're random letters. Thermal energy is represented by a capital U. The thermal energy, or U, of any system of particles is going to be the sum of the kinetic energy of all the particles. Of course, that's a really tricky thing to find because you can't zoom in and look at every particle and figure out what its velocity is at every moment in time, but we'll talk about how to get there in just a minute. Thermal energy is measured in joules, like all energies, so any kind of energy can be added and subtracted from any other kind of energy. So the tip to figuring out thermal energy is remembering that temperature is proportional to the average kinetic energy of a system by that Boltzmann's conversion that we learned in the last video. And so that means that temperature is also going to be proportional to U. So when an object increases in temperature, it's going to have more thermal energy as well. The thermal energy, because it is the sum of all of the kinetic energies, is also going to be linearly proportional to N. That means that the more molecules or particles in a system, the more thermal energy we're going to have because we're adding up more pieces to that puzzle, more things that have kinetic energy. There's kind of a little hacky equation. This is not on the equation sheet, but in general it should make sense. Thermal energy is equal to the average kinetic energy times the number of molecules in the system. Of course, some of those molecules have more and some have less, but it doesn't matter what the individuals do if you know the average. Some examples of some thermal systems in sort of increasing thermal energy order. A popsicle would have a very small amount of thermal energy because it is both very cold, a low temperature, and it's not very big, so it doesn't have that many particles. Cup of tea has more thermal energy because it's hotter. It's still a relatively small object, but it's hotter, so each particle inside that system has more kinetic energy on average than the popsicle. A glacier might not seem like a system that has a lot of thermal energy. All of the particles have a relatively low amount of kinetic energy, but there's so many of them that since we're talking about the sum of all of them, we're still going to have a lot more thermal energy in a glacier than we have in a cup of tea. But of course, something like a volcano is going to win because we've got a lot of average and we've got a lot of particles. So let's talk about what we would mean when we talk about open and closed thermal systems. A closed system is a system that is not exchanging thermal energy with the rest of the universe. Another way to look at this is delta U, or the change in the thermal energy in the system, is 0. It's kind of hard to make a thermally closed system. We have to have a perfectly sealed, rigid, airtight box. We can't allow things to go in or out because everything has thermal energy by virtue of the fact it has particles that are moving. You would also have to prevent anything from going through the walls of the container as far as energy goes. So we can't let mass go in or out, but we also can't let energy go in or out. So we can't let light or heat or any other kind of energy go in or out of the walls. So of course, this is not realistic for the real world. But if you could make a system that was closed thermally, then you would have delta U is 0, which would mean that we have a constant temperature because those things are proportional to each other. Open systems are much more common, of course, and that means that thermal energy can be moving in or out of the system. Either via mass that's coming in or out, which is less common, or the temperature of the system is changing. And if the delta U for my system is positive, that means the temperature of the system is increasing. And of course, if delta U is negative, that means the temperature of the system is going to be decreasing. So when we have open thermal systems, that means that thermal energy is transferring between two systems, right? The universe is closed, but we could have two open systems that are passing thermal energy back and forth between each other. And this will happen if the two systems have different temperatures, okay? And so if you have two thermodynamic systems at different temperatures and you bring them into contact, then energy is going to move from one to the other until the two systems come to a new stable equilibrium temperature in the middle. There's a couple nuances in here, right? First thing, this is intuitive, right? If you take a coffee cup and an ice cube, they're at different temperatures, and put them in contact, they're gonna hang out and swirl around and mix together until finally they're at a single temperature together. So that's what we're talking about. But one little nuance is that doesn't mean the systems will have the same thermal energy when we're done, because one system might have more mass than the other. So what comes to equilibrium as temperature, or average kinetic energy, will be equal, even if the total kinetic energy, the sum of the kinetic energies, is not. Another point that we'll talk about at the end of the slideshow is that when we talk about the movement of energy from one system to another, it's always going to go from the hotter system to the cooler system, and there are three ways by which this can happen. The first way is something called radiation, and we'll talk about that in the next slide. The second way is called convection, and the third way by which two thermal systems can kind of equilibrate themselves is called conduction. So radiation is a process I'm going to define today, but we're actually going to talk about it a lot more in the spring when we get to modern physics. Radiation is the process by which photons of light, so little pieces of light energy, leave the particles in a system, and that's going to reduce the total energy in the system. So light is energy, so if we let energy get out of a system, we're going to have less total energy in the system, and that means the temperature goes down as well. Interestingly, all objects are spontaneously radiating. That means light is shining off of every object in the universe. This is known as black body radiation. So even if something doesn't look like it's sending out light, because it's not sending out visible light, every object in the universe is actually spitting out photons all the time. So the thermal energy of every object in the universe is decreasing. You see this very obviously for a star, right? The light that we see from a star is a process of black body radiation. And we see that light because the star is really, really hot. That means the photons that are coming off are actually within a wavelength our eyes can detect. People are also black body radiators, but we don't tend to see light coming off of a person because we are sending out a different color of light, specifically infrared light, which is a lower energy kind of light. But there are cameras that can detect that. So you're a black body, everything around us is a black body, and that means that everything is losing thermal energy by radiation. The second process by which thermal systems can equilibrate is called convection. Convection happens when you take systems of liquids or gases and you combine them in like a single container. And since there aren't any boundaries between the systems anymore, what happens is the warm and the cold particles move around and mix. You've seen this every time you've looked at a pot of water or your cup of coffee, right? What happens is the heat source basically gives energy to the nearby particles, and then they have more energy, which means they move faster, and so they move to a different spot in the system, and their spot kind of gets replaced with colder particles. There are convection cells. We use that to kind of heat our houses. And the same thing is going on inside of our Earth. We have these cycles of heating at the bottom and then pushing that hot fluid or hot whatever it is to a different location and letting the cold fluid take place. So anytime we have bulk movement, that means the actual pieces of the system are moving around, it's going to be considered convection, the convection process. The third process to move energy from system to system is called conduction, and we're actually going to spend the most time on this process in this unit. So conduction happens when you have two objects that have a solid boundary between them. Now we know that even something that looks solid has moving particles in it, and that means that when two solid objects touch each other, the particles at the edge of one of those objects can actually collide with the particles in the other object. So there's collisions that happen between two objects. And in those collisions, you can transfer thermal energy from one to the other. So here's a diagram that shows this. On the left, we have a hotter material that is shown in red. So that means those particles have a lot of energy. They're moving fast. And we're going to bring up and touch it with a colder object on the right. So those particles have lower energy and they're moving slower. The hot particles on the left collide with the particles, the slow particles at the boundary, and during that collision, they transfer some of their momentum, they transfer some of their velocity, some of their kinetic energy from the red to the blue. And so when we're done, the blue ones are moving faster because they got whacked really hard, and the red ones actually slow down a little bit. We have a special name for this kind of energy that's moving through two surfaces by conduction, and it's called heat. And that's really annoying because you guys have used the word heat wrong, it turns out, a lot of times in your life. It doesn't mean the same as temperature. Heat is very specifically something that an object can gain or lose. Okay, we can gain heat from another system, we can lose heat to a system, but you can't have heat. Heat is going to be a new variable. We're going to use a Q for it. And it is a kind of energy, so it's represented with the units joules. And really it is a change in energy, so it's a delta energy from one system to another. You can have positive or negative Q. You can't have positive or you can't have negative energy, but you can have positive Q because it's how much we're gaining or losing. So a positive Q would mean an object that gains heat energy. And a negative Q would be losing heat energy. So in the diagram shown, the red object above has a negative Q because it's going to lose energy in those collisions, and the blue object will be gaining Q, as you can see by that flowing of heat from one to the other. If you had a closed thermal system, the overall Q would be 0. One object can gain some thermal energy, but the other object will be losing the same amount of thermal energy. Of course, it's hard to make a closed system in the real world, but in general, if you wanted to have a closed thermal system, you would insulate something really well. So something with a lot of padding or insulation prevents Q. It prevents heat from moving out of the box, right? You might have two objects in the box. They can move heat to each other, but if we insulate the box, then heat, or Q, is 0 overall. There's a very silly equation on the equation sheet that has one very specific use. And I'm going to tell it to you even though it's a relatively useless equation in the big world of physics. But it is on the equation sheet and it'll pop up on the test. So there is an equation that literally can only be used for this single thing. Figuring out the rate of heat transfer through a surface by conduction. Okay, that's the only reason to use this equation. It's a rate, which is Q over T. So it's how much heat per second is moving through the boundaries between two materials. If you think about the times in your life you've experienced conduction, when you're trying to pass heat through something, the relationships that contribute to how quickly the heat can move from one object to another should be relatively intuitive. For starters, there is a linear relationship between the difference in temperature of those two systems. So if you put something really cold on something really hot, a lot of energy moves, right? Because the particles have vastly different energies on the boundaries of the surfaces. So we have a big Q. One is gaining a lot, the other is losing a lot. If you have a very small difference in temperature, two things that are exactly the same temperature, put them next to each other, nothing really moves, or whatever moves, moves back because they have the same temperatures. So that's linear relationship. The second relationship is the surface area in contact. So if I'm trying to pass a lot of heat, the best way to do it is bring a lot of that surface in contact, because that's like more particles that can collide. This is why a burner on a stove is really big, right? And you want big bottoms on your pots because it passes the heat more efficiently from one to the other. So, you know, if you had really tiny pots, it would take a long time to heat up your water. Same thing with windows in a house or a building, right? The bigger the window, the more heat passes in and out, which is sometimes a good thing and sometimes a bad thing. The third thing is something known as the thermal conductivity of a material. And this basically has to do with how fast can the particles transfer the energy from one side of the material to the other side of the material, or the boundary material that you're trying to pass the energy through. And this is like a material constant. Some materials pass energy through them really fast and others don't. So for example, metals are good thermal conductors, right? They have a high value of K, which means if I'm trying to get energy from my stove to my water, I make a pot out of metal because it easily, quickly lets the Q flow from the hot burner to the water that I want to heat up. I wouldn't make a pot out of wood because wood has a low K, because that means it would take a long time to move the energy from the stove through the wooden pot. And then the last thing is the thickness of the material you're trying to pass the energy through. The thicker the material, the longer time it takes to get the energy from one side of the material to the other. So the thinner the pot, the quicker the material is going to, or the heat is going to go into the water. So that is inverse, because the bigger the thickness, the smaller the amount of heat per second that passes through. This is the way the equation looks on the equation sheet. That thing on the left is a rate, right? So it's Q per time, it's heat per time. And then on the right are all the three variables, all the variables we mentioned, 3 linear relationships and 1 inverse relationship. The last slide in this slideshow addresses briefly the question of why does energy move? I think we can all agree that it does, but the why is actually a really big, complicated question in physics, and I'm not actually going to answer it in this slide. You'll have to wait for future physics classes. But the short answer that pops up sometimes on this test is the word entropy. If you've heard that word before, you may know it's loosely defined as chaos or disordered or randomness. And so in general, systems are considered ordered or low entropy if the hot and cold particles are separated from each other. This is like the clean room, okay? Things separate. And they're considered disordered or a lot of entropy if everything is crazy and mixed together. There is a law of thermodynamics called the second law of thermodynamics that states, so this is just a fact to know, that the disorder or the entropy of any system is going to always be spontaneously, that means on its own, increasing. In other words, things will always become more chaotic on their own over time. It never becomes randomly more organized, right? You never walk into your room and the wind happened to blow everything back to where it started. It is possible to decrease entropy of a system, so it's possible to clean the room or separate the particles, but the energy and the effort required to do that process creates more chaos some other part of the system of the universe. So this is decidedly not a conserved variable. The delta energy of our universe is always positive. It's always getting more and more chaotic over time, and that's the reason why energy moves. Okay, we say that this is the reason why energy always moves from a hot system to a cold system, because that's the only way that entropy in the universe can be increasing. Okay, we've hit the end of the slideshow. This is one of my favorite Calvin and Hobbes cartoons. Take a second and read it, and hopefully you guys are going to keep your magical snowflakes alive through our schooling system and not letting entropy get you too early. Thanks for watching.